Thank you, Manjunath, for reminding. Okay. So as I said, in this example, you can see the variety of spatial resolutions. As you go from left to right, the spatial resolution reduces. Means what? The lesser number of dots are used to represent the image which is on the rightmost side. So the first image on the leftmost side is represented with the help of 2050 dots per inch. The second image is represented with 300 dots per inch. Third image what with 150, and last image with 7 to 72 dots per inch. And you can easily observe the difference between the clarity. Uh, you can see on this uh, ring on the top of that watch, the gray level transitions are very smooth. However, if you go to the right side, and eventually here it becomes almost observable. The gray levels, transition of gray levels are annoying, and here those are not at all acceptable. So the part of boundary of every image is that black box that you see on a boundary. That is not part of an image. That is just added to have a clarity or the isolation between those two different images. Okay, and that's why the quality of that black outer border is not degraded, because it is not part of the image. It is just for the visibility. And then we saw the tonal resolution, where I explained that tonal resolution means how many gray levels or how many intensity levels we are using in the image. If we use larger number of intensity levels, the transition from the color to color will be smooth. So in general, we need at least 8 bits to represent gray level image, so that it will become it will be good to view at. So 8 bits means 2 raised to 8 number of intensity levels. That means 256 number of intensity levels will be available, from dark black to pure white. So as you can see here in this image, the traversal of intensity level will be like this. So the path I'm talking about is like this, then this, and this, because these these images are derived from some book, and how they are printed in that book, the same way I have copied here in the PPT. And that's why while discussing, please make a note that the path of traversal from the image will be like this. So this is the first image. Let's call it image A. This is image B. This is image C, D, E, F, G, and H. I think I made a mistake. Yes, I made a mistake. I made a mistake. Wait a minute. And the mistake is, this is image A, this is B, this is C, and this is D. And the same way, E, F, G, and H. Okay. So in the first image, if you observe, there are only two intensity levels. Which are those? The dark black and pure white. Only two intensity levels. And this image does not convey much information from that. Okay, if you look at the image B, you can see that here at this point, at this point there is a dark black line. Here you can see there is a pure white. So instead of having only black and white, there are two more intensity levels. One is whatever is there inside this skull, the bright gray level, and one is on the outer side of the skull, that is the little darker gray level. So if you observe in this image carefully, you will see that there are only four intensity levels. There are four intensity levels. That means this image, this particular image, has four intensity levels. So to represent this image, we need at least 2 bits to store all four intensity levels. 0 0 means pure black, 1 1 means pure white, and in between you have two more intensity levels, the brighter and the darker gray level. Okay, so 2 bits are sufficient to store this image. So as you can see in the first image, either we have black color or we have white color. So black will be represented by 0 bit, white will be represented by 1 bit. So this image can be represented with only 1 bit. So every pixel is of 1 bit. So here there will be one pixel, it is 0, the next pixel is 0, the next pixel is 0, and so on. When you come here, this pixel will be 1, the next pixel will be again white, that is 1, the next pixel will be again black, and that is 0. So pixel by pixel, you will use 1 bit to represent and to store that image. Okay, if I go ahead with the C image C, you will see that instead of having only 4 intensity layers, here you will have 8 intensity levels, and to represent 8 intensity levels, you need to store that image by using 3 bits. So here we see that there are totally 8 intensity levels. So this image is with the help of 3 bits. So you can see that as we move to the higher number of bits, the intensity levels are increasing, and image gray levels and the information carried from the image is becoming more and more appropriate and convenient to look at. So further, if I go here, I will have to use 4 bits because there are total 16 intensity levels. We cannot easily identify all the 16 intensity levels as we go ahead with the number of bits. But at a lower level, we can identify some sorry, 2, 4, and 8 intensity levels. So here we need 16 intensity levels. Here 32 intensity levels. This is E. Then uh, after 32, 64 intensity levels, here 128 intensity levels, and here 256 intensity levels. So to store the 256 intensity levels, this image should have been represented with every pixel using 8 bit. Okay, so if I use 8 bits to represent one pixel in this image, then to represent uh, complete image, I will have to use 8 multiplied by 8 bits multiplied by total number of pixels. This many number of total bits will be necessary, and hence the storage requirement of this last image will be much higher. And you can have a look at a quality. You can have a look at the quality of the image that is being shown. So there is no much difference when you represent with the help of 128 intensity levels and with the help of 256 intensity levels. But in some cases and in some images, the difference may be slightly noticeable. So that's why it has been chosen that 256 levels or 8 bits are sufficient. If you go beyond 256 level, the difference will not be so noticeable, and it will be like unnecessarily wasting the storage. So after 256 level, what will be the intensity levels that you can have? After 256 levels, what will be the amount of or the number of intensity levels that you can have? Can you type in a chat box? 512 number of intensity levels. So to represent a 512 number of intensity levels, we need to use 16 bits. And by wasting means you need to use a double storage as that of the current storage. Instead of using 8 bits, if you use 16 bits, the storage requirement will be doubled. And with that double storage, what you can get is little improvement in the image, which is not at a good choice, because if you are wasting double storage and if you are getting very small improvement in the image, don't go for it. Okay, so optimum choices use at least 8 bits to represent gray level. uh, Wait a minute, someone is trying to join. Can't. Anyways, I waited for some time, but the person is not joining. Let's continue. So I hope you understood the intensity resolution. We discussed about representation of an image, and today we also discussed that if there are L intensity levels, then we have to use K bits. So K bits to represent M cross N number of pixels, where M number of pixels in a one row and n number of pixels in a one column. So total number of pixels are m cross n, and every pixel is represented by k bits. So this represents the total number of bits needed to store that image. This is a simple table which is showing that idea. So capital N, let's say we are having the image of square size, or the image of a dimension of same as square. If there are n pixels horizontally, then there are n pixels vertically. So basically a square image. So n by n will be the number of total pixels, and multiplied by k will represent the number of bits needed to represent that image. Okay. So now you can see if there are 32 bits, then 32 multiplied by 32 will be the size of the image. 32 multiplied by 32 will be the size of the uh, or the number of the pixels available in the image, and uh, there are 4 bits. If we are using 4 bits to represent a single pixel, then total number of pixels multiplied by each pixel represented by 4 bit, that gives us total number of bits 409. So this way you can read the table and you can get an idea what will happen if we increase the number of bits. So for example, suppose image has 1024 pixels. Listen very carefully. Suppose image has 1024 pixels, that is in one row. Then in total image we have 1024 multiplied by 1024. That is n multiplied by n, as you can see here. N multiplied by n. Total image will have n multiplied by n pixels, and then multiplied by k bits. So let's say if we are using 2 bits to represent the image, 2 bits to represent the image, then this is the total storage requirement. How much is it? Almost, almost. How much is it? Can you tell me? 2 GB, somewhere close to that, right? And if I use 3 bits to represent that same image, if I use 3 bits to represent the same image, it has improved, or sorry, the storage requirement has been changed to suddenly almost about 3.14 GB. So you can have a clear idea that even a 1 bit increase in representing a particular pixel in an image can cause a total image storage requirement uh, suddenly increase from 2 GB to 3 GB. So that is not at all acceptable. Okay. So this is not actually 2 GB and 3 GB. Why? Because it is not in terms of bytes. It are These are actually number of bits. So you have to divide by it, and then what you will get is a in terms of bytes. So my mistake. I directly considered that as a memory, but it is not memory. It is only number of bits. So number of bits can be converted to bytes, and then you can talk about the memory storage required. So we discussed this all in the last session, and basically image processing is if you have some intensity level at coordinate x comma y. We have discussed the representation of an image where that we saw that image is nothing but different intensity levels at positions x comma y. So if we transform or we perform some operation on that, then the new intensity levels will be obtained at those coordinates x comma y, and that is called as a new image or transformed image. That is called as image processing. There are various applications of image processing. We are not going in details of that, but you can simply have a look. Document handling, such as digital signatures, signature verification like this. It can be used in biometrics where iris recognition, hand recognition, face recognition, or thumb scan, signature recognition. So this is one of the scenario shown where how a person is identified. This is how different kind of matching are used in the fingerprint identification. So it's not necessary to go in details of all of this. Just to have a idea that how vast image processing is. So object recognition, where you can easily identify the object if you have multiple reference views of the object. So how that object looks like in a different positions. If you have already the stored data with you, and then if I give the same object, maybe in any orientation, you can easily identify that yes, this is a pen, or this is a pencil, this is a chair. You can identify that. Indexing into databases, color and texture identification. So many things can be done in a defense defense department. Image processing even can be in a dim light. You can use image processing to identify the location and the capacity of tanks. Aerial photography is a challenging image processing field, and it's always used to monitor the crops, to monitor the traffic in particular area, to visualize the location of water resources and so on. In underwater also, image processing use some kind of sound navigation and radar. You might have heard about it. Sound navigation and radar, sonar system, where ultrasonic imaging is used, where ultrasonics are transmitted, and the property of ultrasonic to reflect from the multiple surfaces will be different, and accordingly the image will be formed of the object from which that ultrasonics are reflecting back. In space also, you can have image processing where the uh, small aircraft like structure, or you are more familiar with the something called as a uh, what I'm saying, drone. I'm talking about drone, so you are more familiar with drone. So in the space also, you can have some kind of structure which is same as a drone, and that can be used for aerial or space photography. And this is the application where traffic monitoring is being shown. This is the application where face detection is shown. Detection means only the face is detected. What, which person is it, that is not being identified. So face detection is different, and face recognition is different. Face recognition or the person recognition means you recognize who that person is, and the face detection means you only detect the faces in the crowd, so that for example, if you want to count the number of people in particular area, so you can use the face recognition. You recognize number of faces and you count the number of faces. So in a face recognition, it doesn't matter which position the person is standing in, whether he is facing the camera or he is facing to the left or right. You can identify them. So accordingly, we program and we count number of faces. So face recognition means you identify the particular face, which person is it. So in that case, you will have to use multiple samples of every person being stored, and then you match the parameters of current face with the stored faces, and you identify which that person is. So there are multiple other things. You can just have a look. In this example, you can see the human activity recognition tracker is being shown. You can see that in the first image, the person on the left side is carrying something. It is shown by the blue color, and the object is shown by the green color. So it is identified that the person one is moving from the left to right in the periodic, sorry, right to left in the periodic motion, and it does not carry anything. But the person zero is carrying some object, and he is moving from left to right. In the second image, we see that they are interacting, and in the third image, we see that the person zero has moved in the same direction, as he was moving earlier, and person one also moved to the same direction as he was moving earlier. But now the object is in the hand of person one. So while interacting, they have interchanged, or maybe they have exchanged something, and that way the human activity can be recognized. The breast cancer also can be recognized. I have another image also where some kind of image enhancement operations are done, and uh, that way we can identify some kind of diseases. Here you can see that the background, what you see is actual image, or the actual physical things which are there on the table. But the coffee mug or the coffee kettle that is shown here, it is a artificial object which is introduced in the scene. So it's not an actual object which is available, but it is introduced by using digital image processing, and this is a artificial object. So next we will see something called as a neighborhood operations in the images. As the name itself suggests, you might get idea that what. Wait a minute. So you will get idea what the neighborhood means. Please someone unmute and say something. Am I clearly audible? Hello, hello.
Yes, sir.
Audible, sir. Audible, sir.
Okay. Okay. So neighborhood operations. Uh, Basically, we will see uh, the relationship between pixels, and under that we will have neighborhood, that is four neighbor, d neighbor, and 8 neighbor. We will see adjacency, that is 4 adjacency, 8 adjacency, m adjacency. We will see connectivity between pixels and components. We will see paths, and we will see regions and boundaries. So we will talk about one by one. We will see first neighborhood. The neighbors of a pixel p at coordinate x comma y. What is basically this, and that we will see now. Suppose this is a small image containing, let's say, only 3 cross 3 number of pixels, that is total 9 number of pixels, and let's say there is a pixel p, at the center. Then the four neighbors, I'm talking about this thing, the four neighbors of pixel p are denoted by n4p. N4p is basically a set. N4p is basically set which tells us what are the neighbors, or what are the four neighbors of the pixel p. And the four neighbors are basically located at x minus 1 y. See what I said? I said pixel p is located at x comma y. So x minus 1 comma y. What will be the pixel at x minus 1 comma y? If I am saying this is a pixel at x comma y, and I already told you that this is the x direction in the image, and this is the y direction in the image. This is x and this is y. So which will be the pixel at x minus 1 and y? Which will be this pixel? X minus 1 and y. Y is not changing, but only x is reducing. Means what? You are talking about this pixel. You are talking about this pixel. I hope you are getting idea. So this pixel, then x plus 1 comma y means x is increased and you are in the same y. So you are talking about the same y location, but you are increasing the x. So you are going downward, and that means you are talking about this pixel now. Then third pixel is x y minus 1. So x is fixed, y is reduced. So you are talking about y minus 1. That means this pixel. And x comma y plus 1. So x is the fixed, but y is increased. That means you are talking about. So the four neighbors means four neighbors of a pixel p, nothing but immediate left, immediate right, immediate upper, and immediate lower pixel of that current pixel p. These are called as four neighbors. So if I represent some set called as n4p, that represents the four neighbors of a pixel p. That means these all pixels, if you write in a curly bracket, that set is called as four neighbors of the pixel p. Please say whether you understood this or not. Unmute and say understood or not, so that we can go ahead.
Understood, sir.
Okay. So if you want to remember what four neighbors are, you just, yeah, you just think of the horizontal and vertical immediate next pixel. So in a horizontal direction, immediate next pixel is this and this, and in vertical direction, immediate next pixel is this and this. Okay, so these are the four neighbors. Similarly, we have D neighbors. As I said, there can be four neighbors, there can be D neighbors, or there can be eight neighbors. So the diagonal neighbors are called as D neighbors, and the name is very straightforward. You are going to look in the diagonal positions. That means the inclined positions. So x minus 1, y minus 1. So this is x comma y. X minus 1 means this particular row, and y minus 1 means this particular column. So you are talking about this this point, this pixel. Let's say this is the D neighbor, x minus 1, y minus 1. Then x plus 1, y plus 1 means you go x plus 1, that means downward, and y plus 1, that means rightward. So for this pixel, if you go downward and rightward, or rightward and downward, you are talking about currently this pixel. So this is the diagonal neighbor. As you can see, you are talking about the diagonal. You are talking about this and these positions. Similarly, x plus 1, y minus 1. X plus 1 means go downward. Y minus 1 means come leftward. That means you are talking about this pixel. And x minus 1, y plus 1. X minus 1 means you go upward. Y plus means you go rightward. And that means this pixel. So the set NDP represents the diagonal neighbors of a pixel P. The bracketed term is, we are talking about neighbors of pixel P, and the subscript D represents, you are talking about the diagonal neighbors. So this also is very clear. And eight neighbors means all the neighbors surrounded on the particular pixel are called as eight neighbors. So as I said, we generally talk about the pixel which is having the regular dimension in all the sides, and hence it's generally a square box. So how many total neighbors you can have in the square box? You can have immediate neighbors on the left and right, top and bottom. You can have neighbors on the corners, 1, 2, 3, and 4. So you cannot have more than 8, right? So maximum number of neighbors you can have are 8 neighbors, and that's why they are called as 8 neighbors, and they are represented by set n at p. What do you think these 8 neighbors will be? These 8 neighbors will be nothing but collection of all the neighbors which you have found in the 4 neighbor, and all the neighbors which you have found in the D neighbor. So if you find four neighbors, if you find diagonal neighbors, then if you write all of them together, that becomes 8 neighbors. So n at p is equal to collection or the union of set containing four neighbors and the other set containing d neighbors. Okay, so here you will have all these neighbors on the boundary of this center pixel p. All these neighbors are the part of at neighbors. Okay, then we will talk about adjacency. Uh, depending on what kind of neighborhood we have, depending on what kind of neighborhood we have, there are three different kind of adjacencies that are being discussed: four adjacency, eight adjacency, and m adjacency. We will see what are they. Let V be the set of intensity values. So you will be given with the set V, and the idea of adjacency will be very clear when we will take a real time example with actual values, some matrix, and by now you just listen what it is. So for adjacency means the two pixels P and Q with the values from V are four adjacent if Q is in the set N for P. So let me uh, represent one image once again of a size 3 cross 3. This is the image. This is one pixel and this is one pixel. This is another pixel here. This is another pixel here. Another pixel. Okay. Now two pixels P and Q. Let's say this pixel is P and this pixel is Q. Then these two pixels which are having values from V. So as you can see, this pixel is having value 1, this another pixel is having value 1, and both of the values are actually present in this set V, right? So if both the pixels P and Q have values from V, then we can say that these two pixels are code adjacent if Q is in the set of N4P. Meaning of this is if Q is fourth neighbor of a P, or in other words, I can say that P is in the set of N4Q. I can talk in the reverse way also. Q is in the set of N4P or P is in the set of N4Q. The meaning of this is if the two pixels P and Q are four neighbors of each other, then we can say that they are four adjacent. So now you can see here this pixel and this pixel, are they four neighbors of each other? What are the four neighbors of the center pixel? Let me change the color of a pen and show you. What are the four neighbors of the center pixel? This, 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 and this. So for this pixel P, the fourth neighbor is pixel Q. Can I say one of the fourth neighbor is pixel Q? Can I say this? Yes. And similarly, if I mark all the four neighbors of that other pixel, that is Q pixel, then fourth neighbor of Q pixel is this, this, and one of the pixel that may be here, which is not shown, or maybe that is not available in the image. So it's not necessary that all four neighbors will be always possible. For example, in this pixel, we don't have four neighbors at this side and this side. Okay, so that is possible. So currently for this pixel, we have only three four neighbors, and one of them is a P. Okay, so for P, one of the four neighbor is Q, or for Q, one of the four neighbor is P. So they are four neighbors of each other, and both of the values are present in the set V, and hence we can say that pixel P and pixel Q are four adjacent. Okay, so we will stop here today, and we will continue from the four adjacency in the lecture that we will have at the 3:15. Okay, if you have any doubts, you can ask. Otherwise, you can leave me. Thank you.
No doubt, sir.
Okay.